We all have heard that cloud is infinite. If you need more capacity, what do? Just scale out. Well, it feels true for a while until the bill arrives or your service melts under a surge. Hi, I'm Praval Panwar. I work at Microsoft. I lead Metrics Observability org. Today, I want to challenge the idea that infinity is a strategy. In the next 35 minutes, I would like to burst this myth and show you the cost and reliability implications of this myth on your services. We'll also look at some of the examples from operation-heavy industries that don't have the luxury to pretend that cloud capacity is infinite. But before that, I want you to take on my scaling out journey. This was my house growing up. When I was a kid, my house, my backyard, and my neighborhood was my known world. As I grew, my city became my known world. And if you are wondering which beautiful city it is, city's name is Jodhpur. It is situated in the northwestern part of India, in the state of Rajasthan. And if you ever get a chance, you must visit. All right, then for my schooling, I moved to the United States, and this country became my known world. As I was growing, my exposure grew as well, and the planet Earth became my known world. Later on, I learned more, and the whole universe became my known world. It remained like that until I saw this picture captured by the Hubble telescope of a galaxy that is 13 million light years away. So now this is my new world, actually. All right, so you saw my own scale-out capacity just kept growing as I grew. Now I would like to draw parallels from this example. What you're seeing on screen is a journey of any successful service or a product. It all starts with that first Hello World program that you write on your local machine. Then you write more code, and your service is ready to be deployed to a single server. Now it's getting famous. You want to deploy it to more servers because you have more traffic. And eventually, you want to take it to the cloud because you want to get the benefit of elasticity and auto-scaling. Ultimately, you can see that this service is actually on a journey of going to infinite. Now, both from my example and this service example, you can see that scale-out can appear infinite at first glance. However, our finances are not infinite. I mean, I wish they were, but they are not. We don't have a money printing machine sitting at our homes. And this is exactly what I call the fallacy of infinite scale. In my observation and experience, I have realized that the problem is mindset and not the tooling. The cloud is infinite is a very comforting idea. However, every real system has its limits. You have quotas, you have budgetary constraint, you have noisy neighbors, and well, of course, you have people. This idea can actually foster a mindset which often leads to insufficient planning and overspending. On the screen, you can see that's what people are talking about it in our industry. One person is saying that cloud isn't infinite anymore. The other one calls out there is no such thing as infinite compute. At the bottom of the screen, you can see, according to Forbes' recent survey, 70% of companies accept that they are paying for cloud capacity they are not even using. So the message is very consistent that infinite scale is indeed a myth. Capacity is finite because physics is real, and most of us are massively over-provisioned. And as I said earlier, this illusion of infinite scale also comes with a very hefty bill. Our industry is actually realizing this problem. Companies are acknowledging it, but they're finding it very hard to manage the cloud spend. According to a Flexera report, 84% of companies accepted that they struggle to manage the cloud spend and the waste. Now, you may ask, if it's such a trivial problem, why are we not solving it yet? Because it's not a trivial problem in certain situations, and I'll talk about those. Few weeks back, I wanted to buy tickets for FIFA World Cup happening at the US. I was ready, sitting at 10 a.m. in front of my computer. I had the website open, and as soon as tickets became available, I was ready to click. However, I could never complete the transaction. I retried again, the same outcome. At that moment, I realized that the problem was not that the tickets were already sold, but the problem was that the system was overwhelmed. And what happened that day was not necessarily a bug. It was a capacity problem driven by uncertainty. When tickets open, usually demand does not arrive gradually, it arrives in bursts. Maybe there are 2 million users, maybe there are 10 million users. You will never know for sure. You can try to do probabilistic modeling and prediction, but you will never know the exact number of users that will hit your system. So what do you do in those cases? You usually provision for average demand. However, the system becomes overloaded during these sudden bursts. And this is what capacity planning under uncertainty looks like in the real world. When demand is unpredictable, your job is not to provision infinite capacity. It is to provision it intelligently. We'll look at certain examples as we move forward, but I want to give you one more example. And I'm sure nobody wants to go back to 2020, but I do want to talk about the toilet paper COVID fiasco. And I'm pretty sure people will relate with me. I remember going to grocery stores in the toilet paper aisles and finding that those aisles were wiped out clean. It did not happen once, it happened repeatedly. And ultimately, it became a shared global experience. Now, the problem was not that people were buying more. So for every individual, it made sense to buy a little more. However, collectively, it became a problem because it created bursts of traffic. Now, the production capacity had not suddenly collapsed that time. The infrastructure was still there, but what changed was the demand behavior. So the system was not broken. It was operating as it was designed, but just outside its expected demand range. That proves that there are limits of known and limits of unknown that may impact your capacity planning. Now let's tie it back to the SRE paradigm where we say 100% reliability does not exist. Systems always operate in a permanently degraded mode. If you even want to try get to 100% reliability, you would need infinite redundancy, infinite failover, and ultimately infinite capacity. That's impractical and impossible to achieve. That's my point. Capacity planning operates under the exact same constraint. You will never have 100% certainty about the load your system will receive, so your goal is to provision it intelligently, and you want it to operate within the known range and gracefully degrade outside of it. Another problem that causes a lot of cloud waste is resource misallocation. When you are faced with uncertainty, like what we saw before, usually there are two ways to design your system. The first one is you either build a fortress or you try to walk the tightrope. If you build a fortress, you're misallocating resources through over-provisioning, and if you try to walk the tightrope too closely, you are misallocating risk, and the system becomes fragile. You can have big fortresses for the most critical services or for industries such as healthcare or hospitals, but for services such as recommendation engine, you may not need to build a fortress. So you need to understand the service fragility and operate within the acceptable risk boundaries. Here's the million-dollar question. How do you balance risk and capacity? In this talk, I will try to walk you through certain examples and lessons that you can learn and adopt them. But the most brute-force answer to this question is you do right-sizing. Right-sizing is a very basic concept, yet it is very difficult to achieve. In the ideal scenario, reaching to a right-sized state would mean that your resources are optimized for workload demands while you balance cost efficiency with higher performance. And it's never going to be an absolute number. So it changes depending based on your system demands and behavior, and you may need to have a dynamic approach. But before I go any further, I want to ask you a question. Have you ever thought how operation-heavy industries such as airlines, power grids, logistics actually perform their capacity planning? Because, as I said earlier, they don't have the luxury to pretend that capacity is infinite. I mean, you cannot build an airplane like overnight, like how easily you create compute. You cannot, build a power grid even in a week. So we'll look at some learnings that we can, adopt in our scenarios. But before that, I want to ask you a question. Imagine I'm an airline company, and I'm offering every seat in every flight just for $99 always. How would you compete with that? This is the same question what American Airlines executives were actually looking at in 1980. After deregulation of the industry, there were certain companies that were offering exactly the same fare. And American Airlines, being an established leader at that time, they saw that their market share was going down, and they had to do something about it. But what they did was really interesting. They actually turned to their computer system, to a massive mainframe system called SRE, and they tried to find answer to this question. How many $99 seats should we sell to fill the plane, and how many should we hold back for business travelers who will pay $300 just the day before for the same seat for the same flight? This is what capacity yielding looks like. What American did there was to turn guesswork into calculations using data. They deployed a system that used historical booking data to forecast demand and price seats dynamically. They modeled no-show rates per week, per route, per day of the week. So essentially, if you expect 10 no-shows, you sell 10 extra tickets. This is what overbooking is. And American accepted that this approach caused, they added actually $225 million in their bottom line numbers. So essentially, if you look at the timeline, 1960, that's when the electronic reservation started. Early 80s, that's when the superfare was introduced. Mid-1980s, that's when Americans started using forecasting models and overbooking. Within few years, it actually proved its impact and essentially became a global standard. And here's the kicker. These same techniques are still being used today in the industry, although they are far more optimized, but the concept is still the same. So let's look at a little bit deeper what ARIMA is. ARIMA stands for Autoregressive Integrated Moving Average. The details are not important, but what important is that these models learn pattern over time. They understand trend, seasonality, weekday, weekend effects, and they give you a forecast range, often in form of an uncertainty range. So airlines use this approach to find the answer to the question, how many people will show up for a certain flight? So they plug it in, ARIMA, and then they actually forecast passengers for a flight. On top of it, they also use booking curves, where they compare the live booking to historical curves and adjust the forecast. So learning for us is, we can also try to use some time series model to forecast your traffic per service, per region, and also you can use booking curves to forecast launch traffic right before, say, a Black Friday sale or some company events that you're going to have. Another approach they use is explicit overcommit. If you look at the formula, it says total seat booked is C plus K, where C is total number of physical seats, and K is an overbooking constant. Airlines try to optimize for K so they can have more revenue. And if they see denied boardings or it becomes too costly, they actually back off. This is what probabilistic overcommitment is. It's a controlled data-driven risk trade-off. Now let's apply it to our scenario. Imagine in the same formula, you have C as your physical or CPU or memory on a host, and K is your virtual capacity that you are trying to allocate via overcommit. You should try to find answer to the question, what is the probability that all workloads will spike together? You can set K to keep your overload probability below a chosen threshold, and this is a very strong technique. Using this, you can pick overcommit factors from your utilization distributions, and you can even define your SLOs and risk around it. All right, so now you have done overbooking, you're overcommitted, But what if you don't have a system to track uncertainty in your system? Back in 2007, on 14th of February, JetBlue kind of faced similar thing. At that time, they were shiny new airline. They have fancy leather seats. But on that particular day, there was a storm rolling in the New Jersey, New York area. And they decided to do something very different. They said, we are not going to cancel any flights. Let's see how it turned out for them. On that day, they had over 156 flights scheduled. However, only 17 of them flew. Majority of them were actually stuck on the tarmac for hours. It created really bad impression to their passengers. On top of it, they had no clue where their 11,000 pilots and crew members were. They had no way to communicate with them. It took them 6 days to fully recover from this. During that time, executives of JetBlue were actually sitting in the office trying to enter this information in a spreadsheet manually. And that's how the real-time true tracking database came into existence. And that is why crew rotation optimizations are even used in the industry today. So if you look at it, it's a simply mixed integer programming problem. We have flights form a graph, plane and cruise are flows with constraint, and if disruption happen, you need to re-optimize in real time with minimum cost recovery plan. So let's apply it to our scenarios. In our scenario, services gonna be flights, compute resources gonna be crews, and region and availability zones gonna be airport. So when and if a region goes down, you have to find the answer to the question, do you have a plan to reroute traffic and workload in real time? Essentially, you can use these techniques to schedule workloads with anti-affinity and decide what to cancel first. The point is you should assign priority to your workloads so that you can figure out what's the lower priority workload that you can cancel first. All right, so from airline industry, we looked at bunch of algorithms. Essentially, all of these push us away from infinite scale thinking towards right sizing of a cloud. Let's see another industry, power grids, and see how they perform real-time balancing. But before that, do you actually know a real power of a tree? Back in 2003, a single tree in Ohio caused power outage for 50 million people, and it caused a monetary impact of $4 to $10 billion. Let's look at what happened on that day. On August 14, 2003, at 4:06 p.m., a single tree sags into a power line and trips it. So remember, it's just one line and one tree. Usually, power grids are designed for this, and that's the whole point of having a network and not a single power line. In usual situations, within a minute, the command center would receive an alert. However, that particular day, there was a silent software bug that prevented those alerts. Now, within the next minute, at 4:08, more and more power lines started to getting tripped. Thankfully, by 4:10 p.m., Operations Center finally sees the alerts, but what they see were a bunch of red dots. They had no clue what had happened, what was the sequence, or what's going to happen next. By 4:13, that's like what, within 7 minutes, cities like New York, Cleveland, Detroit, Toronto, they lost power, and more than 250 power plants had to be shut. It impacted more than 50 million of people, and it took 2 full days to fully recover from this. So investigations happened, and the conclusion was that the grid violated N-1 constraint. Let's look at what N-1 is. According to this principle, your system must survive the loss of any single major component, be it one generator, one transmission line, or one substation. If losing one thing causes everything else to collapse, you really don't have a resilient system, you just have a house of cards. But as they say, failure is often trigger for innovation. So the power grid industry rebuilt. They now mandated real-time monitoring system so that they don't fail silently. They require to run N-1 contingencies and simulation. They also came up with advanced algorithm to keep grids operating inside safe limits and came up with automatic load shedding schemes. So what are learnings from this and how we can adapt? So essentially, the idea is you need to define n-1 for your stack, and you must meet SLOs if one region or availability zone or a data store fails. You may also have reserve margin and spending reserves for your most critical services. However, you have to be very diligent and thoughtful here unless you will start creating a very massively over-provisioned system. As I said earlier, you also should assign priorities for your workloads, so you have an automatic load shedding strategy for your lower priority work. All right, so now you have implemented n-1. What else can go wrong? Well, what if there is some error in your forecasting? On February 15, 2021, Texas had they faced a severe winter storm. Texas actually planned for 67 gigawatts of winter peak. However, the actual demand turned out to be 76. And due to the severe weather, 40% of their generation capacity also came down. And within 4 minutes and 30 seconds, many grids collapsed and millions of people actually lost power. So that 9 gigawatt gap is exactly what short-term load forecasting is supposed to close. If your capacity planning is based on last season times some number, and you never update the model, you will get surprises, and those surprises are not going to be pleasant. Learning from it, power grids now use continuous load forecasting models with real-time weather data and advanced neural networks. So if you look at the formula, they define inputs as history, weather forecast, calendar days, and they use some neural network, often an LSTM or a hybrid model, and they get output as a predicted load over next hours or day, with, of course, some error distribution. Now, let's apply it to our scenario. You can replace L with QPS or CPU utilization per service and region. You replace weather with external drivers such as marketing campaigns, product launches, events, or seasonality, and maybe use a very simple model such as Profit or some LSTM that can give you better forecasting results. However, you have to treat load forecasting as a first-class discipline with continuous model updates. You apply the feedback and use real-time input to get most accurate forecasting numbers. So for power grid industry, we looked at n-1, continuous reserve margins, and predefined load shedding. Essentially, these techniques tell us to treat capacity as a risk management, not infinite elasticity. So using these techniques, we can also try to right-size our clouds. Let's look at the next industry, logistics. Again, the toilet paper example. I'm sure nobody wants to go there, but let's talk about it one more time. So in traditional forecasting, what you sold last March and the March before that, you use those patterns and come with a number what you would need in this March. Then you apply some seasonal adjustments, you apply some trend smoothing, and you have your forecast. And it works. Well, most of the time it works. However, March 2020 was not like any previous Marches, and I'm sure everyone can vouch for it. What happened in that month? The demand for multiple commodities has exploded, you can see there, mainly because households were using 40% more than normal, because everybody was sitting at their houses, right? That caused the demand planning error to go up to 59%. However, even in this scenario, certain companies actually did much better than the other. Do you know what was the difference? They actually used a technique called exponential smoothing. In this technique, you give more weight to recent data than the older data. By using these techniques, they were able to reduce the forecast errors from 20 to 60% down to 4 to 9%, which is incredible. Here is the formula for it. Essentially, if you look at the formula, you'll see recent data gets more weight. However, the older data decays exponentially. Using this technique, you can have better stocking decisions when you combine it variability metrics and lead time metrics as well. The idea is you can use this technique for your internal services to create capacity baselines or auto-scaling targets and be a little more intentional about it. All right. After 2020, 2021 was also no fun. I'm pretty sure you can recall how difficult it was to buy a car in 2021. Do you know what exactly happened that time? Here's the timeline. So in early 2020, due to COVID, car sales were plummeting, and automakers thought, like, hey, we don't need to make those many cars, so let's cancel our chip orders. Because they try to run lean. However, by late 2020, the demand went back again, and they reached out to chip manufacturers asking for more chips. Interestingly, in mid-2020, due to everybody was working from home, there was a huge demand for laptops and electronic equipments, and the chip manufacturers actually assigned that capacity to those industries. And finally, when automakers reached out to the chip fabric manufacturers, they said, well, we don't have capacity for you, you better get back at the line. Because of this, auto sector had to face more than 100 billion revenue loss. However, they learned from it, and then they started using more conservative safety stock policies. Now, if you look at the formula, safety stock is extra inventory that you held to cover your uncertainty due to your demand and lead time. In the formula, you can see Z is how safe you want to be. So you can pick, say, I want to be 95% service level. Then you'll have a Z value of 1.64. Sigma here just defines the measure how much demand actually jumps around. All right, so we're going to do an interesting exercise now. We'll do some napkin math. Imagine I'm launching a service, and I have a forecast average demand of 10,000 requests per second. My demand variability is around 2,000 QPS with provisioning lead time of 15 minutes. That is essentially how long it takes you to spin up new nodes. And then you have lead time variability around 5 minutes. I want to be a little conservative, and I want to go with target service level as 99%. So essentially what I'm saying here is I want less than 1% of chance to hit hard capacity. Now here's the formula, and we plug in some numbers. First, Z is your service factor. As I said, we are choosing 99%, so the value is going to be 2.33. It is essentially how many standard deviation you want to go above the average. Now let's plug in rest of the numbers and do the math. The result is you would need 118K requests for your buffer capacity. So our baseline was 10,000 QPS times 15. That's around 9 million requests during the lead time. You have your safety stock. To get the total capacity you should provision for, what you do is you sum up those numbers. And then in our case, it's going to be 9.1 million requests over that 15-minute window to survive 99% demand spike. So that's the number you have to provision the capacity for. This is an incredibly powerful technique and tool. By using this, you can achieve higher reliabilities even during the downtime, or if your service is moving from one region to another or from one cluster to the another. It essentially tells you how much extra capacity and queue headroom you should use. So you can use this to size buffer capacity and queues on demand variability and with your error budget. All right, so now we have added safety stocks, ran probabilities. But what happens if the vendor that you're using is actually down and you don't have a backup? Same thing happened with Toyota. On 11th of March 2011, Japan had seen a very bad earthquake, and majority of Toyota assembly lines and manufacturing plants were down. And it actually took them 6 months to fully recover. When they did the investigation, they found out that majority of their vendors and suppliers were actually in the same region, and they were also impacted. So essentially, they redesigned their policies. But if I try to tie it back to our SRE principle, you need to have redundancy, then you have a backup plan, and then you need to have a backup plan for the backup plan. But you got to be very diligent here as well, because you have to treat risk versus cost trade-off. You have to take it very seriously, because every layer of redundancy will cost you money. So how do you go about it? If you're a startup and you have limited runway, your budgets are tight, what matters is speed to market more than perfect reliability. You can accept to run a little leaner and take more risks. So essentially, your trade-off is going to be you move fast now and invest in resilience as you grow. On the contrary, if you are an established or critical platform, You have regulatory compliances to meet, you have millions of users on your platform, and your high revenue at stake, then you actually need to invest heavily in redundancy and accept higher cost. So we saw a single supplier, of course, can be a single point of failure. You should prioritize your customers and SKUs under load, and think about multi-region and multi-vendor for your most critical dependencies. These lessons from logistic industries actually tell us how we should learn to optimize for scarcity rather than planning to go infinite. To recap, these are concrete questions you should ask yourself. What is your real capacity? What is your failure mode? And what do you drop first? Most importantly, is all of that information written down? Because I'm really sure for most of the systems and services, the answer is going to be no. And in worst case, it might be living in somebody's head. So first, you find out answer to these questions. Then you look at the SRE primitive mapping that I've just told about, and you pick one or two strategies that resonate with your scenarios, and then you simply apply. By doing that, you would embrace data-driven capacity planning to achieve cost-aware right-size cloud. So to close, essentially, you need to learn to work with intelligence constraint. You have to treat capacity as a finite resource. You learn and apply lessons from other industries and avoid the infinite cloud mindset. You may ask why we should do that. Because the best teams don't rely on infinite scale. They design for finite reality. Thank you very much.